All right, the final talk of the morning session is Robert Neagu from KU Leuven, and he will speak about quasi-free flows on Cuntz algebras.
Thank you, and I'd like to thank again the organizers for putting this together and giving me the opportunity to give this talk. Hopefully there are no controversial opinions here, but we'll see at the end. Okay, so I'm going to talk about flows, and this appears already this morning, and this appeared in Yasuhiko's talk. So flows are just like continuous actions of the real numbers. It's a group homomorphism, and it's continuous in the sense that for any this map from real numbers to a evaluation is non-continuous. Okay, and the disclaimer is I'm interested in like the classification of such things, but I'm going to be very concrete. So the class of flows I'm interested in is this class of quasi-free flows, and this is exactly the class of group actions if you're on the Jamie was talking earlier this morning, and really it's called quasi-free because the action is given by a unitary representation. And the situation for flows is somehow like easier and harder at the same time. It's easier in the sense that you can really write this like in a very, very nice way. And the reason is that whenever you have like a unitary representation of the reals into like P of H, or H is finite dimensional, you can use Stone's theorem to say that any unitary is like really an exponential with the same self-adjoint, and then you just diagonalize that self-adjoint. So really, this e to the it lk are just like the eigenvalues of each ut in the representation. But they might be harder because usually it's harder to classify flows because of the continuity requirements. Okay, so I'm going to think of this class, and I want to understand when maybe two such flows are equivalent. So if I change the parameters, it's totally unclear if the flows are the same or not. And for me, well, equivalence will be cocycle conjugacy, which well appeared in Jamie's talk. It's not too important really for this talk, but you can think of like having an almost equivariant isomorphism, and almost it's sort of twisted by this one cocycle, but it's not very important. Okay, so I want to ask when two flows are cocycle conjugate. So what are some positive results here? Well, one of them is, of course, it depends on the tuples, right? So if you know that each of these tuples generate the real numbers as a closed subsemi group, then these flows have like a very strong property called the Rocklin property, and they are all cocycle conjugate. So it's not very important what the Rocklin property is, as you'll see later why. But it's very strong, and somehow, yeah, you don't see the difference between them. And as an easy case, just let's think of n equals 2, which just means that the parameters have different signs and they are rationally independent. So the rational independence is really like not to get a periodic flow. Okay, so it's kind of like an outerness condition. But this thing that combined with different signs, it's a bit more subtle. Okay, so this is what this gives this Rocklin property. So natural question here is like, well, what if the parameters have the same sign? They're also rationally independent. What happens there? And I don't want to define the Rocklin property, but I'm going to tell you what it gives and what's the difficulty when you don't have it. And what it gives is that when you have the Rocklin property, this cross product is simple and purely infinite. So this is kind of the strange thing with like locally compact groups. When you have a discrete group and you have a Kirchberg algebra, as Jamie defined it, but if the action is outer, you always get one of these simple purely infinite cross products. But if your group is not discrete, this outerness is not enough, right? This has to do with KMS states, if you're familiar with that. Okay, but the Rocklin property somehow tells you, well, we're in that nice case, everything is simple purely infinite. So you kind of expected that it's easier to classify things. But without this cross product can be stably finite, which is quite strange, maybe, if you think about it. And it is indeed. So now if you focus on O2, which is kind of the easier case, well, let's just simplify the situation and say that one parameter is 1 and the other, we can do that by scaling the flow. So based on this lambda, let's see how this works. Well, this cross product, well, if lambda is negative and irrational, right? We're in the situation of rationally independent and different signs. The cross product is O to tensor K all the time. Well, I told you that these are classified, so you should expect that the cross product is always always the same? Well, if lambda is positive, you get something different, but generically. Okay, so it's quite difficult to compute this cross product in general. You should know what it is by classification, let's say, but it's very difficult to show that the cross product has the classification requirements. So it's known generically that this is W tensor K, and well, this W is kind of like a stably finite analog of O2. You don't really need to know what it is. The point is that it has 0 KT array, so it's kind of like O2, but it's stably finite, and it has a unique trace. It has no projections. It's quite a strange object, but it has a unique trace, and now you should expect that there is extra information here. And the extra information should be that this conjugacy class now of alpha gamma should be encoded somehow in this extra trace information. And what I mean is that, well, whenever you have such a cross product, let's say by R, you have a canonical dual action on it. And this canonical dual action well interacts with the traces, right? So, and because you have something stable, you shouldn't expect that this trace is fixed. It's actually probably scaled. And this is the idea here. Now, if I want to classify, let's say, such flows alpha gamma, or show that they're in some kind of like classifiable class, I could try and classify the dual actions, right? So in this case, because I know if I have two dual actions which are co-cycle conjugate, then my initial action. So because okay, so I somehow transfer the problem to like classifying dual actions. Well, I kind of know at least generically that this should be W tensor K. So what I need, I'm looking for a theorem. Do I have any kind of theorem which classifies flows on things like W tensor K? And we do. So Gabor proved something quite general. So we don't, again, it's not necessarily important what stable projections and all of these things are. The point is that W tensor K falls into this class. And I should point that this is the reason I want to focus more on O2. Precisely this KKAA0, okay? Because if you have ON, and you take the cross product, you'll have non-trivial KT. So it will not fall under the umbrella of this theorem. Okay, so this tells you that in a situation like that, if you have two Rocklin flows, again, whatever that is, you should expect that the interaction of the flow with the trace gives you the classification. And in our case, for O2, Kishimoto and Cuntz established like quite early what this is. So if you have one of these